Back in August 1961, contractors installed 4 heavy industrial steel blast doors manufactured by the Mosler Safe Company. The primary vehicle entry door alone weighed 25 tons, measured 18 inches thick, and operated on hydraulic hinges, engineered to swing shut with less than 50 pounds of manual force during a total electrical failure. These doors secured Project Greek Island, a highly classified continuity of government bunker built beneath the Greenbrier Resort in West Virginia. The facility presents a structural paradox, maintaining absolute airtight operational concealment while constructing industrial-scale defensive architecture. To understand the friction between secrecy and scale, look at the excavation footprint. The design required a 112,544 square foot subterranean envelope, buried 720 feet into the hillside, directly beneath a luxury commercial hotel frequented by international diplomats. To mask the massive influx of communications hardware and maintain the bunker for 3 decades, the government established a dummy corporation. Forsyth Associates operated on paper as a humble television repair firm, allowing highly cleared technicians to live and work on the resort grounds without raising local suspicion. Achieving operational secrecy at this massive structural scale mandated absolute isolation from public infrastructure audits. Every utility, from water to electrical conduits, had to be seamlessly integrated into the hotel's commercial grid and concealed behind automated pneumatic isolation valves. The engineering specifications were matched by a strict human capacity limit. During the 1962 Cuban Missile Crisis, the bunker was placed on high alert to accommodate a maximum of 1,100 personnel, specifically structured to house 435 House representatives and 100 senators. The technicians on site maintained a cryptologically shielded communications network. Legacy teletype hardware and secure microwave arrays linked the Subterranean bunker directly to other strategic command nodes like Mount Weather and the Raven Rock Mountain Complex. Consolidating the entire legislative branch into a single fixed coordinate introduces a second strategic paradox: the inherent risk of democratic legislative continuity relying entirely on concentrated target vulnerability. By gathering the entire succession line of Congress into one physical location, the strategic profile becomes all or nothing. If a localized structural failure occurs at that specific coordinate, the result is total political decapitation. Engineering a facility to maintain the continuity of a democracy transformed it into the nation's single most critical vulnerability. The target specification for Project Greek Island required the facility to withstand a nuclear blast overpressure of 25 pounds per square inch at a distance of 15 to 30 miles. When a surface detonation occurs, the kinetic energy is transmitted into the Earth as a hypervelocity shockwave that immediately crushes the surrounding rock strata. As kinetic energy moves deeper, the initial shockwave rapidly decays into an elastic plastic stress wave. The transmission of this stress wave through a 720-foot soil and rock overburden is highly nonlinear. The kinetic and plastic dissipation energy within the soil structure system behaves according to specific mathematical constraints. This graph charts the scale distance equation, z equals r over the cube root of w. It defines how standoff distance and TNT charge weight interact to deliver force. As standoff distance decreases, kinetic strain on the bunker escalates exponentially. The mathematics prove that static deep earth facilities are geometrically limited. A fixed-depth concrete bunker cannot indefinitely outscale the increasing yield and accuracy of modern explosive weaponry. Inside the bunker, the geometry of the tunnels creates a separate hydrodynamic problem. Confined tunnel geometries restrict downstream pressure release, which converts incoming blast waves into guided shock fronts. Wave scattering physics reveal a hydrodynamic inflection point. When a shock front hits a 60-degree tunnel bend, the primary pressure wave scatters, but almost immediately, constructive interference causes the pressure to rapidly compound just upstream of the bend. During localized interference, a severe acceleration spike is exerted directly onto the rigid concrete tunnel mass. Without complex geometric mitigation factored into the initial architectural blueprint, internal tunnel layouts can inadvertently amplify incoming blast forces past lethal thresholds. The 1960 perimeter walls of Project Greek Island were poured using 3-foot-thick Portland cement and continuous high-yield rebar matrices, engineered to absorb 4,000 psi of compressive stress. Today, structural engineers measure blast resistance using the concrete damaged plasticity, or CDP, failure model. This model exposes the limits of historical monolithic concrete pours. To survive modern kinetic penetration, structural engineering relies on hybridizing metal and polypropylene fibers into the mix to actively mitigate explosion-induced plastic strain. This dual bar chart shows the exact mixture requirements for modern structural resilience. By integrating barite aggregates and boron carbide powder, the concrete achieves a 24% increase in compressive strength and a 42% increase in bending strength compared to historical standards. Beyond the chemical mixture, structural resilience requires spiral reinforcements to physically confine the inner structural core of the concrete. During a live blast test, standard reinforced concrete experiences catastrophic surface crushing. By contrast, an optimally mixed, spiral-confined core maintains its structural geometry. The historical monolithic pours of the Cold War lacked this internal spiral confinement, making them mathematically incapable of surviving modern groundburst scenarios exceeding 50 psi. Beyond kinetic survival, these structures must prevent the transmission of gamma and neutron particles. Modern optimal concrete mixtures establish a strict pre-blast radiation shielding baseline. This radar chart details the pre-blast reduction metrics achieved specifically by adding heavy barite minerals and boron carbide. This mixture successfully reduces the transmission ratio of gamma particles by 19% and neutron particles by 26%. But the true test is post-blast capability. Forensic audits expose a severe anomaly in standard concrete. After absorbing an explosion, normal concrete develops structural microfractures that allow a lethal 98% of emitted rays to pass straight through the barrier. This side-by-side data visualization contrasts that failure rate against modern engineering. Only a slab utilizing both an optimal chemical mix and a confined structural core retains 94% of its radiation shielding efficiency after taking blast damage. If a bunker survives the kinetic impact of a detonation, the facility is compromised if resulting microfractures permit lethal radiation transmission into the occupied envelope. Keeping the occupants alive also requires continuous atmospheric management. Historical specifications mandated a positive air pressure differential of 0.5 inches water gauge, processing 80,000 cubic feet of air per minute. Maintaining that internal positive pressure requires precise fluid dynamics to balance the intake against dual-stage HEPA and catalytic oxidation scrubbers. During a severe external atmospheric overpressure event, any failure in the automated pneumatic isolation valves creates an immediate backdraft contamination risk, forcing chemical or radiological agents directly into the airlock envelope. This extreme mass air movement also targets the mechanical vulnerabilities of the primary blast doors. High-velocity gaseous explosion products and propelled debris interact with the steel plating in highly nonlinear ways. This diagram maps force distribution data from the Ferguson Structural Engineering Laboratory, tracking dynamic shear stress across the W, S, and C-shape longitudinal stiffeners. The data shows hydraulic actuators represent a single-point failure mode. Under intense shock motions, mechanical bearings snap. Unreinforced actuator bearings render a 25-ton defensive door permanently sealed or completely inoperable immediately following a primary kinetic strike, trapping the occupants inside. The rapid deployment of advanced deep earth penetrating ordnance completely invalidated the defensive utility of these high-mass static bunkers. In response, the government issued Presidential Policy Directive 40 and the Federal Mission Resilience Strategy. These policies outline a shift away from the physical consolidation of government branches. The modern framework relies on decentralized, highly redundant networks focused entirely on preserving abstract mission-essential functions. When physical transitions are required, agencies do not use static legislative fortresses. Instead, they utilize highly specialized, active subterranean nodes dedicated to secure, high-volume data and logistics processing. A prime example is the Office of Personnel Management's records facility, operating 230 feet underground in a former limestone mine in Boyers, Pennsylvania. The Boyers mine houses 26,000 file cabinets and relies on golf carts for transit. It functions as a climate-controlled subterranean city for critical administrative data, entirely distinct from the heavily armored, high-stress survival bunkers of the Cold War. Other contingency facilities, like the Rocket Center Co-op site in West Virginia, are strictly designated to host the Emergency Federal Register, ensuring the constitutional rule of law survives even if the physical capital does not. We leave you with the final declassified edge case from the Greek island dossier: the unresolved structural realities of long-term moisture management and catastrophic concrete carbonation in decommissioned underground bunkers, stripped of active HVAC systems.